Got it. And here comes, hello everyone on YouTube. We're just getting started. Welcome, welcome. All right, welcome everyone to the next Water, Wetlands, and Watersheds seminar for spring 2023. We are all virtual today, but hopefully we've got all our students here in the Zoom room, and we've got all y'all out in YouTube land. Excellent, I see YouTube is streaming. Good to see you all today. It's my pleasure to introduce our speaker today, Dr. Devi Kadyampakeni. Dr. Kadyampakeni is an assistant professor of soil, water, and ecosystem sciences at the IFAS Citrus Research and Education Center, which is down in Lake Alfred. If that's right, Davey, down in Lake Alfred, right?
Yeah, that's correct.
His research interests focus on best nutrient and water management practices in horticultural cropping systems. He has more than 10 years experience working on irrigation and nutrient management, particularly of citrus and vegetables. Dr. Kadyampakeni has written or edited 4 books and 7 book chapters and published more than 60 articles in refereed journals. He's an active professional member of the Irrigation Association. I bet most of you didn't know that there was an association of people doing irrigation, but indeed there is. Very important here in Florida. The American Society of Horticultural Science, Florida State Horticultural Society, among many others. And he's the chair or past chair of a number of groups, including the American Society of Agronomy, Sensor-Based Water Management Community, and the American Society of Horticultural Sciences Citrus Working Group. So with that, Davey, the floor is yours. For all the students online, please feel free to put your questions in the chat or to save them for the end. And let us know if you have any trouble hearing or seeing anything, drop me a note in the chat. All right, go ahead, Davey, floor is yours.
All right, thank you so much, Dr. Kaplan, for your kind introduction. And when Dr. Kaplan invited me to give this talk, I had to get something that I thought would be appealing to the community and the audience I'll be talking with. So you notice I work on a couple of things. So a lot of crops, a lot of soil measurements. But for this talk, I want to focus a little bit on one of the niches I focus on, which is parameterizing, measuring, and modeling water and contaminant transport dynamics in the Vadose. Yeah, so when I talk about contaminants, I'm looking at, because someone say, "Oh, look, are you looking at, what toxic substances? Is it heavy metals? What is it?" Yeah, so for me, contaminants will be fertilizers. There would be pesticides. There would be herbicides. Those are the contaminants that I deal with within my management system. So let's go ahead and let me give you a little bit of an overview of what I will be talking about. So to make sure you follow me, I'll spend a few slides talking about the soil characteristics of the production systems I deal with. Before what about the nutrient leaching and all the water movement dynamics and all that. And then I will also highlight the measurements we take. So we use a lot of heavy instrumentation to make sure we can measure some data in real time and continuously. Then I'll also highlight some of the nutrient management practices. So as you might know, in Florida, we have mostly sandy soils where we grow crops, whether it's citrus, whether it's vegetables, or whether it's other row crops. It's mostly in sandy soils. So optimizing the nutrient management practices is a key thing. And then, of course, this is maybe where everybody's looking at, so, okay, then, so what? Yeah, so I want to make sure I walk you through some of the scenarios we have looked at, trying to quantify nutrient leaching dynamics and water movement dynamics. And then I'll show you some of the quantitative models we've used to be able to understand those decision systems. And that'll be it for the day. And I'll be happy to have a further conversation later. So just to begin with, this is the table that I want everybody to pay attention to. So where we grow citrus, predominantly we have around close to 400,000 acres in the state. Those 400,000 acres are dominated in what we call the antisols in the Central Florida ridge. So between Orlando and a town called Sebring, that's considered the Central ridge, well-drained sandy soils called antisols. Very sandy, low organic matter, low water holding capacity, moderate acidity to a little bit of alkalinity. And then we have the southeast flatwoods. So where we have somewhere around 4 piers, some of you know the southeastern part of the state. Also very sandy soils, low organic matter, low water holding capacity, and then of course also a little bit of moderate acidity, but a little bit elevated pH. Then in the southwest flatwoods, we are looking at very heavy sand, but also a little bit of very low organic matter, low water holding capacity, and a little bit of the pH and all that is similar to the one on the ridge. So this is something that you have to keep in mind, because as I go forward, I will keep referring to these characteristics as I talk about them going forward. Another thing you have also to bear in mind is that for the soils that are in the southeast and southwest flatwoods, they are porous red. So in the southwest part, we have what we call the spotted soil. So the second row here in the table, while the southeast flatwoods is mostly dominated by artificial. So that layer that restricts drainage is called the BT horizon. So it's somewhere between 70 centimeters to 1 meter below the ground surface. Same thing with the spotted soil. And the only difference between these two layers is that for the spotted soil, it will have a little bit higher organic matter. For the artificial, that layer will have a little bit of higher clay. So that's also another distinction you have to bear in mind. But I'll end up referring to this eventually. So just to give you an idea of what we look at, so as you can see in this figure, this is a typical central ridge soil. So as you can see, the A horizon, the E horizon, below the A, so the A is the top layer, the E is the middle one, very heavy sand, and that's where we get so much drainage occurring in there. And then, of course, low cation exchange capacities, low water holding capacity, and most acidic. And the typical soils we find, in case you use the USDA NRCS service, they'll classify that as the Statler fine sand, Basinger fine sand, Candler, or Tavares. So those are typical soils for that. If you go to the southeast flatwoods, so you're looking at the artificials. So those ones who have also, you see the coloration changes a little bit. So they'll have the top layer, the A horizon, and then that'll be followed, as you can see on the right, by the E horizon, well drained. But then, of course, if you get to 70 centimeters, one meter, you get to the PT horizon. So the characteristics that I have highlighted here, so they're also, these are poorly drained soils with an acidic horizon, the BT horizon. Then they have low organic matter, low cation exchange, lower holding capacity. The pH tends to be higher. So it will be largely above 7, but slightly below 8.5. And the typical sandy soils like that are Boca, Palo Pau, Pineda, Riviera, and winter soil soils. So when you start looking for such types of soil, this is typical what you see. And then, of course, another example of the sandy soil you see in the southwest part of the state is where you have the spotted soils. So these are typically present in the southwest part of Florida. They have a sportic horizon, as you can see, which is the BH on the right. So the top layer is the A horizon with high organic matter. The E is where we have a lot of sand. That's where most of this drainage occurs, where we have all these dynamics of nutrient losses and chemicals drained to the groundwater. And then, of course, it has low organic matter, low cation exchange, low water holding capacity, and then, of course, it has moderate acidity to moderate alkalinity. Typical soils like this include the Mokale fine sand. Here, in this picture, it's a Mayaka sand. And another one is called Oldsma. There's another one called Pomona or Simina or Wabasosaurus. These are the examples of this type of soil. So with that in mind, whatever I'll be talking about starts from the fact that we want to talk about different components of the water that we apply to the plants. So in this little schematic I have, you are looking at the inputs of water to the Vadose through irrigation or rainfall, and then through subsurface flow, especially where you have the high water table, where you have capillary rise. So you're having a high water table and then feeding into the root zone of the Vadose. And then you're also looking at outputs of water from the soil surface. So for example, through evaporation, or by the plant itself through transpiration, or through deep percolation, where the water is now moving below the root zone into the groundwater, or you are having subsurface flow or lateral flow getting out of the root zone. And more importantly, you notice that you might also have losses due to runoff. So runoff is not typical in Florida because we have sandy soils, but of course, deep drainage is typical because it's mostly sandy soils. So those inputs and losses that are characterized here, through irrigation or the I, or rainfall through the P, which is precipitation, and then of course DP through deep percolation, and the runoff as RO, capillary as CR, and then subsurface inflows and subsurface outflows. So that leads us to understand that fluxes that go into the root zone or the bed zone will be represented by this little equation here, very basic equation. But I think if you start paying attention to hydrological inputs into the models you use for evaluating water losses or water inputs into a system, you will notice that this equation is very useful. So ET would be the evapotranspiration, combined loss of water through evaporation and transpiration. And then, of course, the I would be what I talked about. Oh, excuse me, I went too far. So the I would be the irrigation, the P will be the precipitation or rainfall, RO will be the loss through a runoff, DP will be the deep percolation runoff, losses. CR will be an input through capillary rise, and then, of course, either you'll be having changes in this subsurface flow. If you're having inflows, that'll be an addition, so it's a plus. If you're having subsurface flow exiting the system, that'll be an outflow. And then, of course, changes in the soil moisture content within the bed. And then you can represent that through this model that FAO prepared and allow it, whereby you're looking at a big cube, and then you're looking at those inputs of water through irrigation or rain, or losses through evapotranspiration from this cube. And then if you overfill this cube, you get runoff. And if you just fill to that top of the cube, that's saturation. But if you are getting to somewhere where the plants didn't love it, you are getting to fill capacity. So you didn't, that's where you want to be. But sometimes you don't irrigate that enough. You just get where the plants is getting available water to some level. Then you have what we call a threshold moisture content. So the difference between fill capacity and the threshold moisture content is what we call readily available water. But it happens that you want to be able to decide when to irrigate. So there'll be a point just below the threshold that will be using that to differentiate and determine how often to irrigate. So you use sensors and other tools to be able to let the system know when to apply additional water. And then you don't want to run out of water by using up most of the available water. So if you do that, you end up getting to waiting point. We don't want to get there. And then, of course, inputs of water at the bottom will be capillary rise, losses to the cube will be deep percolation. So I love this schematic because it helps me understand better and anybody else to follow what we talk about. On the bottom here, you see I have a little graphical presentation of how you can track the soil moisture changes. So we had a sense that 6 inches, 12 inches, and then 8 inches. So the green bar, line is 8 inches. That's about 45 centimeters from the soil surface. So a little bit elevated soil water content. And then the red line is at 12 inches, and then the dark one is at 6 inches. So the active root zone. So because of the trees using up most of the water, you see that a lot of active dynamics of water use and by the tree roots. So to measure the soil moisture, we use the curve of sensors. So as you can see here, I just provide some examples. Mostly we use capacitor sensors. Some use handheld sensors, but I prefer this because you can connect this to data loggers. So these are typical examples of capacitor sensors, and others use TDT acclimate sensors, especially where you are doing irrigation practices where you're applying nutrients with you're putting nutrients via irrigation. This TDT acclimate sensor is very ideal because it tells you exactly how much you're putting in it. It measures soil moisture, it measures salinity, it measures electrical conductivity, and all the temperature in the root zone. So very handy too. And just to give you another overview here in this table, it's a busy one, but I just want to show you some of the tools we also use for measuring. So tensiometers, granular matrix, capacitance probes, time domain transmission, and then time domain reflectometry. As you can see, for our standard source, we normally prefer the bottom three. So capacitance probes, the TDT sensors, and TDR, because those ones are a little bit handy. They require low maintenance. They don't require much calibration. They're high to medium accuracy, and they're suitable for standard source. So that's where we really recommend. In the past, we used to use tensiometers, but not much anymore, because we realize we lose a lot of contact, and our commercial growers and the industry don't really benefit from that. So we have been recommending use of these sensors. And just to also highlight a lot of measurements on the water use aspect. So we use a lot of chemical scientific tools. As you can see in here on the left top corner, we have the chemical scientific data loggers, which are connected to lysimeters at the bottom left corner with the blue tabs, where we can now track water use in lysimeters. We put trees in there, then we can track the leaching in there. We put some port, and then we can also track water use. And you can see a weather station in there, which is helping us understand dynamics of evapotranspiration. And as you can see in the middle, we have a solar panel that you can use in the field to put a data log and connect trees to sensors that track water use over time. And then you can see an example of a sensor put on a tree, like in citrus. And this is typical. You can use this in corn, you can use this in bamboo, you can use this in peach, you can use this in cotton. There are different sizes of sensors, but this is just an example for you to understand. And as you can see on the use of lysimeters, this is a weighing lysimeter technique. It's one of the most preferred and accurate methods for measuring water use in the trees. So this, I just wanted to highlight this to show you some of the measurements we take. And then I also want to show you a little bit about how we install the sensors. So right here, when you are putting the capacitance sensors, we really put them right there in the root zone. You can see the roots, and we dig a little bit into the root zone and put at multiple depths. I usually prefer doing it maybe 6-inch increments, but recently we found some probes that you can put in the root zone that can go all the way to 48 inches. But here I'm just giving you an example of how we install the some of the probes so that we get accurate measurements. And on your right, you see a little bit of the water volume measurements in an irrigation line. So you put some tools that can track the irrigation rate, can track the moisture capacity within the root zone, and then you hook this up, and then you can also connect a weather station nearby to track the evapotranspiration. So all this is important for us to be able to optimize water movement and retention in the root zone. So you see this is a loaded slide, but I just want to show you how much we invest in this. I have so many of these kinds of graphs, but I'm just trying to give you an idea of how we monitor water use using some of these tools. And in this study, we had done a study in 3 parts of Florida: central part, central southwest, and the southwest part of Florida. So this was in Urban Park, in Arcadia, and in Ave Maria. In those studies, we did over about 4 years, but here I'm just showing a few years between 2013 to 2014. And what we're doing, we're comparing water use between their irrigation and then an irrigation frequency that growers use, which is like irrigating every 3 to 4 days, very infrequent. And then we had an intermediate practice where we are comparing whether we can reduce the intermediate practice and use an IFAS schedule, more or less. So what we noticed was that the daily irrigation schedule was much better. It was the one triggering better water use in trees. But when we use the intermediate schedule, or we compare that with an IFAS schedule, which is irrigating every 2 days, we realized that those irrigation schedules were not optimal. So as you can see, except for the middle graph on your extreme right, the rest of the graph showed that the top one was the daily irrigation schedule. The other schedules were not optimal. And we published this work about 5 years ago. So very encouraging results. And in the similar study, we tried to compare the water use and then so much dynamics that happen in the root zone and see if there's any correlation. And what we found was that there was a strong correlation between the subflow and then the water use that that we noticed, and then the soil moisture dynamics. So as you can see on the left, this will be the various treatments. So IFAS irrigation schedule, which is irrigating every 2 days, daily irrigation schedule, which is in green panels, and then the red panel, which is the intermediate schedule, and the IFAS one is the dark panels. What you notice is that the daily schedule retained most of the high soil moisture content in the root zone. So at all the 3 sites. Well, as when you correlated that with the subflow, as you can see on the right, very good correlations, R square 0.9999. I couldn't get to all the way to 1.0, but very strong correlation. So what we noticed is that daily irrigation was keeping water at the top 30 centimeters or the top 12 inches. And that improved performance of trees. And that we saw that there was some level of elevation of so much in the bottom 45 centimeters, especially at Avon Park, where we have well-drained sandy soil. So I feel like there was a little bit of movement of water, but overall, we were able to retain most of the water in the top root zone. So that was good. And just to give you another idea of what we've been tracking, also, there were some studies we are looking at comparing what we call open hydroponic systems. So with macro sprinkler, you will get every day, or using drip irrigation, and you will get every day multiple times to just keep water in the root zone. So one thing we noticed is that when you compare that with conventional macro sprinkler practice, which is CMP, we noticed that all the practices retained water close to field capacity. So the orange line on the left is the field capacity line. And then you can see on the right, the green line is also the one for field capacity. So we were keeping the water mostly just about 7 to 50% in the moisture range between 7 to 15%. So keeping the water either above or close to field capacity. So that was good in terms of optimizing water management. And we published some of this work in the Journal of Soil Science Society of America, in case some of you might be interested. So I was also showing you some of those measurements where we are looking at the soil moisture or the water volume. So here I'm just giving you a snapshot of some of those measurements. So you can see on your right, you have a graph that shows how much water was applied, except for August, where I think the battery died for the data logger. We had to restart it and reset it. But we're tracking the water use over time, and we have kept that going until now. And then you see here, every sensor has a line, so you can track every day the amount of water you're applying. So this is very important for Vadose on water management and even tracking nutrient leaching. And you can even see the battery level of your data logger on the left. You can see that within the snapshot of your data that you're collecting. So I just wanted to share that so that you see some of the measurements we take. And now here is also another way that we have been observing the comparison of water use in trees. So we had this set up in the greenhouse, and we're using lysimbidas, as I'd shown you earlier in some of the pictures. And we're comparing water use between healthy trees and trees that had been influenced by citrus greening. And what we noticed was that we found greater water use or greater crop coefficients with healthy trees compared to those trees that had been affected by other diseases like citrus greening. And one thing we noticed also that that increment was between 20 to 35%, so very significant. So what we noticed is that we might consider reducing the rate of irrigation for young trees that have been affected by citrus greening, as you can see in this figure here. So the red line, as you can see, will be that line for the IFAS water estimation, or water use estimation, and the dot, the solid dot circles and the solid triangles are for either Valencia orange or Harmony orange. That was a healthy tree in both graphs. The empty circles and the empty triangles are for those trees that were impacted by citrus greening. So very fascinating results. We did these studies for about 2 years and documented this in the, as you can see in the article in Hot Technology. Just also to give you another highlight of what we have been tracking, I have several of these kinds of graphs on ammonium and nitrate, phosphorus, and potassium. But here I want to just share a little bit about how we've been tracking potassium distribution in the root zone. So in the top soil layer, as you can see, if you look at the graph on your top left, so we have drip open hydroponic system, and the drip is placed right there in the where you have the dark triangle. And on the right, top right, you have the conventional macro sprinkler, and the weighted area is for the whole solid triangle, where you have a microjet that weighs about 360 degrees around the tree, close to a radius of about 3 feet. And then at the bottom, you see the macro sprinkler open hydroponic system. So the one that was irrigating every day, but irrigating weekly, whereby the microjet was just wearing within a 100-degree area of the tree. So kind of what we call partial root zone drying, just wearing a portion of the root zone. So one thing we noticed was that we found greater potassium. So as you can see here, the dark solid brown is the highest concentration for the potassium. As you go down, the solid dark green will be the lowest concentration. So one thing we noticed was that the variegated zones had better potassium distribution. And we noticed also that those weighted areas for macro sprinkler open hydroponic system and drip open hydroponic system had better root density. So root density will be like the distribution of roots below the irrigated area, showing that there's potential for better uptake compared to the non-irrigated zone. So for some reason, in the conventional macro sprinkler, the tree weighted around the whole radius, but we saw a little bit of lower nutrient content. And we also published this work in the Soil Science Society of America. So just to give you a highlight of the same treatments, the potassium accumulation was a little bit comparable, but funny enough, where we had the lowest potassium distribution, maybe because it was spread around the root zone, we found greater potassium accumulation compared to the two open hydroponic systems. And here I didn't present the result for nitrogen, but nitrogen was the opposite. So we saw elevated nitrogen uptake with the open hydroponic systems by about 45% compared to the conventional macro sprinkler practice. So very interesting result. And here I would also like just to give you another snapshot of what we have been using, or what I've been doing to track nutrient movement in the zone, focus on micronutrients. So I've done desorption studies in the lab, but here I will not share all that, but I'm just showing you some of the measurements I've done in the field, and we try to track this between 30 centimeters from the row or from the plant, 60 centimeters from the plant, and 90 centimeters. And one thing we noticed was that when we compared soil fertilization and then, of course, foliar fertilization, where the foliar is spread on the foliage, but we still ended up getting some fertilizer falling on the ground, we noticed that obviously soil fertilization resulted in the elevated levels of boron in the soil, and the control, which didn't get much boron, had a lot of residual and was compared to the foliar methods. So very interesting results. But one thing we noticed was that for fertilization, we may need to tweak the way we fertilize. That way we can stay within the root zone so that we keep the fertilizer just close to where the roots are, as you can see in this graph on the left, where it's the 30 centimeter depth, I mean, not depth, but distance from the tree. So that's something that you have to pay attention to. Though the patterns were kind of similar, but not much nutrients were observed at the 90 centimeter distance from the tree. Now, with those measurements, we have also done some good work with quantitative models, and I would like to spend a couple of slides to just show you some of the observations we've made. And we did some work with what they call Hydras 2 or 3D that was developed in California. And we tried to use that to understand dynamics of water movement, nutrient movement, and tracer movement. So for this, I've selected just two nutrients, so ammonium and potassium. As you can see here, what we measured overall was reasonable, but we noticed that when we're tracking the the ammonium over time between the 0 to 60 centimeter depth, which helped us to the slight overproduction of the cumulative ammonium distribution in the root zone. And this was within 12 days after application. But after about 2 weeks, all that was gone in the root zone. It was all leached. Yeah, and this was published in the Journal of Environmental Quality. And something with potassium, we found a good agreement between what we predicted. So the measured values will be the orange ones, but mostly the dark ones will be what we simulated. So a good agreement, and that's what also observed. Most of it was also leaked after 14 days, largely because of the standard soil characteristic. And then with that, we also have been doing some column studies. So as I started earlier, I was talking about the different horizons, and we did those column studies on the L horizon, the E horizon, and the pH horizon on an emulsifiant site. And we published this work in one of the journals. They call it Journal of Plant Nutrition and Soil Science. And what we did was we picked a sample of soil and then filled it to bulk density, to original bulk density. And then we imposed some process. And then when we were able to impose saturated flow, we're able to mimic the fertilizer solution that we apply in the field in fertigation systems. And then we did this column studies for about a 24-hour period, okay? And then after that, we're able to get effluent about every 30 minutes. So we're collecting intensively over a day. And one thing we used after we did those measurements, we tracked the effluent by chloride concentration and as a tracer and the nitrate concentration. And then we used one-dimensional convective dispersive equilibrium model called CFTIM that was developed by Vanaginichten in California. And one thing we noticed was that within less than 8 pore volumes, we're able to show that there was good agreement between the model, so the solid line is the model prediction, and the empty circles are the nitrate, and the dark circles are the chloride. That we were able to get good agreement between the measured chloride and nitrate, chloride and nitrate content in the effluent of the column. This was within the A horizon, so the top 15 centimeters. Now, when we try to look at the ammonium, one thing we noticed was that in the same top layer of soil, in the top A horizon, we found that there was good agreement of the measured ammonium with the model between the before the 2 pore volumes and after excuse me. I was trying to say that there was good agreement of the model, especially between 2 pore volumes and 5 pore volumes. But before that, before the 2 pore volumes, we found a little bit disagreement. So the model was kind of over-predicting a little bit. And then after 5 pore volumes, it was also a little bit of over-predicting the ammonium. So we suspected that maybe the ammonium, though we are doing this in 24 hours, but somehow maybe it was transforming into nitrate. So that might have led to maybe either over-prediction of the model for the ammonium movement, and then we actually measured less of it. And so here's a normalized breakthrough curve that we're using, that we developed for the chloride, the nitrate, and ammonium for the same top A horizon. And then we also try to track the nitrate movement. For some reason, the chloride didn't come out good, so we didn't find a good agreement, but somehow the nitrate was the one that we're able to fit into the model in the E horizon. So the E horizon is this one, which is very heavily leached. And we noticed that there was also good agreement with the model for nitrate leaching. And we used also the same model, the one-dimensional CDE model that was wrote by Vanaginichten in 1980. And then, of course, within the same E horizon, we also found that some noise, the model was also kind of over-predicting a little bit for ammonium, but we found good agreement, especially between pore volumes 1.8 to somewhere around 4 pore volumes. One thing I forgot to mention is that the R here in the graph, each of the graphs is the retardation factor, and the T would be the pore volumes. I mean the pore volumes, and the P will be the Pecking number that was used for the fitting of the model. And then, of course, I mentioned about the BHO horizon in the Mocalefan sand or the sporosos, where we have this very high clay content. And we try to just track that, that horizon and see what we would observe. But we noticed also a little bit of good agreement between measured chloride and nitrate content in that root zone, as you can see here. Very optimal movement of chloride and nitrate. So we noticed that, okay, we could really use these models if we have these variables measured, the Peclet number, the dispersion coefficient, we know the retardation factor, we know the sorption coefficients of the nutrient or the chemical we are dealing with, then we can still understand the movement of chloride or the nitrate in the Vadose zone. And then finally, we also looked at ammonia. Then with ammonia, we observed that there was a bit of overprediction of the model for ammonium in the BH horizon. So we noticed that largely that was between 1.8 to 5 pore volumes. When actually we're having a lot of this saturated flow, the model was over-predicting movement of ammonium, and still we speculate there was a little bit of either transformation of ammonium within that quick time of saturated flow. At this point, I would like also to mention that in the same study, we had where we are looking at the ammonium and then the nitrate movement, we also tried to track a pesticide, imidacloprid, and in the same column study. So you will see here that the chloride is following the other, the blue panels are the chlorides. So on the left, this will be the A horizon. And as you can see, the chloride was fitted using the CD model, the one I told about, the convective dispersive model. But the red line is the one for imidacloprid, the pesticide. So as you can see, this one we used the one side non-equilibrium model to fit. And one thing we noticed was that the chloride generally agreed with the model, but that for the imidacloprid in the top A horizon, we noticed that we went a little bit higher than regular 8 pore volumes, went all the way to 16 pore volumes. And we noticed that after the 9 pore volumes, the model kind of underpredicted the level of imidacloprid movement. So that's something that we have to consider in the way we use the models. As you can see, these are the parameters for the model. These are the coefficients that we're using for the one-side equilibrium model. So on the E horizon on the right, you see that mostly there's some good agreement. Though for imidacloprid in the between the 1 to 4 pore volumes, we saw that there was a little bit of overprediction by the model. So most of the imidacloprid that was measured was a little lower than what the model predicted. So very interesting. And then when we looked at the E horizon on your left, the BH horizon on your left, and the A, then we also had a combination of the A, E, and BH horizon on your right. We noticed that the chloride, which is the blue panels, and then of course the imidacloprid, which is the red panels, we found that the chloride obeyed the model, kind of made a very good agreement. But for the BH horizon, we also noticed that our measurements a little bit greater than what the model predicted, especially after the 9 pore volumes. So the BH horizon, the O horizon, we kind of actually similarly, we suspected because the A horizon has high organic matter, while the BH horizon has a lot of clay, so that might have influenced a little bit of the reactions by imidacloprid. It was kind of binding to the root zone, to the colloidal fraction of the soil, thereby limiting the losses that we would anticipate in the Vadose. But when we combine the A, E, and BH horizon, getting a portion of each of those horizons to see what we will get. So we had like 5 centimeters of the A horizon, 5 centimeters of the E horizon, and 5 centimeters of the BH. We had more or less like a perfect breakthrough curve. So I really loved this curve. I thought, wow, this is kind of interesting. Yeah, so in a nutshell, we can say that for soils that are used for citrus production in Florida, we need to work on improving the water and nutrient holding capacity. We need to manage them well, use all the sensors and tools we can need to limit nutrient leaching by using sensors, and then of course also by using right fertilization practices, especially irrigation practices, so that we minimize nutrient leaching and water movement beyond the result, as I've demonstrated in most of the slides I talked about. One other thing also we are thinking about when we are happy is that there's an acute need to understand that those components are sort of balance, because when you're looking at those fluxes of water use, water movement below the result, water retention, we should be able to find ways of minimizing water losses and optimize water use efficiency. So right now we have all these experiments looking at mulching the ground cover, or using deficit irrigation. So I did have those slides included, but hopefully in the future I'll be able to share those results also to show how much water we're able to conserve by trying to limit transpiration losses and evaporation losses. And one more thing that I also want to emphasize is that optimal irrigation scheduling along with water use is important. As you have observed that when you use plant-based sensors and soil moisture sensors, then we can track the optimal times of irrigating, and then you can increase irrigation efficiency and obviously limit nutrient leaching losses. And then one other thing we also have noticed is that use of some of the hydrologic models has improved our understanding of when to apply what. So we can understand nutrient movement, especially we've looked at nitrogen, we've looked at potassium, we've looked at chloride as a tracer, we've looked at water. I didn't include water here, but also we have had those data to look at the water movement. That information from hydrologic models can help us understand, especially where we can't really measure the amount of loss, because some of these measurements are very hard to do in the field because we don't have the right instruments. But if you use the models and we have the right calibration, then we can understand how much fluxes, how much water movement, or how much nutrient leaching or pesticide leaching occurs in the root zone or in the Vadose zone of Florida sandy soils. So at this point, I'd like to acknowledge most of my collaborators at Lake Alfred, and some of the colleagues at Southwest Florida Research Center, and some colleagues that have worked in the past and present at the Indian River Research and Education Center, and then obviously also some colleagues on campus in Gainesville from our department, and so many sponsors, so USDA, some fertilizer companies that have supplied us with products, the Citrus Research and Development Foundation, and also the University of Florida Citrus Initiative. And I would also like to acknowledge my team, past and present. As you can see on the left, so mostly that's my current team, and maybe four of them are in this audience here. So Muriel, Kudus, Kondwani, so and then Jose Prieto, and then Devon. So about 5 more were not present when we took this photo because they're either on campus or they're doing their studies online. And a few of these members have moved on. Some of them graduated and some of them retired. So this has been the team I've worked with for the past couple of years, and I'd like to acknowledge them. And I'll be happy to take any questions. And this here is you want to track me further. So you use that QR code. You get my website, my contacts, my email, my Facebook page, my LinkedIn page, my ResearchGate, Google Scholar, and wherever I'm found on the planet. So you'll be able to track me down.
All right, thank you so much, Davey. We really appreciate you. Let's give him a round of applause, either virtually or just, you can unmute and clap. Let me actually let you unmute now. So go ahead. Thank you so much for speaking with us today. Yeah, real claps. Thank you. So we have a question from YouTube, which is sort of rare. We usually have people just lurking on the YouTube, but let's see. We have a question from Jay Nepal, asking if you are aware of any soil microorganism-based amendments that might be helpful for HLB, for citrus greening affected citrus. And this person had a farmer ask them that question recently. You're aware of anything like that?
That's a good one. Yeah, I've heard of some soil microbial amendments that we can use for mitigating nutrient availability. But unfortunately, I haven't been able to do that in my studies, but I've had a few colleagues talk to me about it because we didn't get any funding. I mean, it's very fascinating to do that, but we haven't been able to do an investigation. I wish I could do that in the near future.
Okay. Natalie, do you want to unmute and ask your question? Natalie Salman?
Okay. Hi, I'm here with Megan. I was wondering if how's monitoring sap flow, what does that tell you about irrigation? Does that tell you how water is taken up, or how do you deduce from sap flow of what it says about water?
Oh, very good question. Thank you, Natalie. So with sap flow, what you have learned is that now after nearly 10 years of doing this, what we have learned is that it seems those trees love water to be irrigated somewhere before 9 a.m. Because what we have noticed is that when we track the water use, it starts getting elevated from 9 in the morning all the way to 2 p.m. Beyond 3 p.m., it starts tapering down. So we realized if you apply water somewhere between 7 and 9, then you provide that sweet spot for those roots to get actively into the uptake. So right now, I'm trying to develop a little model that couples root, because we have been also mentioning root growth, so I didn't want to provide all those kind of root data to this audience because there would be just too much biological information. Yeah, so we have been tracking root growth over time. Then we've been tracking so much data over time. Then we've been tracking the water use over time. And we are seeing correlation between those those three variables. And one thing I've noticed is that those subflow values get elevated after 9 o'clock. So it means if you apply water before 9, that will coincide with the peak water used by the tree. So that's how we use the subflow data to be able to decide when to schedule our irrigation. Thank you. I hope that answers your question.
Thanks for the question, Natalie. Thanks, Davey. I just have a general question. You talk a lot about the optimal moisture level to ensure healthy growth and sort of generalize about water savings and things like that. But do you think, are you on the cusp of developing, say, IFAS recommended irrigation scheduling or IFAS recommended nutrient applications that take advantage of all these results you're finding? Improving, I guess what I'll say is directly like nutrient application guidance because you're able to keep more of the nutrients in the root zone and taken up?
Yeah, that's a good question, David. The final part is that I think for nitrogen, we are able to lower nitrogen a little bit and to get the same result with the current recommendation. But the final part is that for the micronutrients, for example, because most of the trees or in citrus I'm dealing with have been kind of impacted by citrus greening. So they lose a lot of roots. So for micronutrients, we have seen that when we elevate the application rate, for example, 3 times to 4 times the current rate, we are getting a better response in terms of root growth. Yeah, so we have realized that we can, it's going to be just maybe 20 pounds of that nutrient per year. So not much, because in the past could apply less than 10 pounds. So we have realized, okay, doubling or quadrupling or tripling micronutrients would be okay. But for the macronutrients like nitrogen and phosphorus, we are still trying to tweak that a little bit. So right now, I wanted to talk about that, but I don't have much results. So we have been lucky to get some support from the legislature. So we are looking at varying rates of phosphorus and varying rates of nitrogen. So across 14 sites in the state. So the Panhandle, the Southwest Redwoods, the Southeast Redwoods, and the Central Ridge. And what we are doing is that we are tracking these nutrients, nitrogen and phosphorus, from 0 to 15 centimeters, 15 to 30, 30 to 45, all the way to somewhere around 90 centimeters below the zone. And then what we're hoping to do is that we'll also take some physical variables like a bulk density, hydraulic conductivity, we'll add all the weather data, we are collecting all the weather data. So hopefully along the way, when we have taken all these physical measurements, we'll add quantitative modeling to it, and then hopefully take the results and then adjust the recommendations. And so we are hoping that we'll provide those data to feed into the recommendations, as you rightly mentioned. So IFAS will be revising some of the nitrogen and phosphorus guidelines for citrus because of the impacts you have had. So some of the recommendations we're using now are really actually not as valid as they should have been for trees that are impacted by citrus breeding.
Sure. Well, I'd love to talk to you more about that. We're doing, of course, some large-scale watershed modeling that has citrus as an important component, and we have to develop some sort of management scheme that represents reality, or perhaps an even improved reality. So let's talk more later. I have a student on here who probably needs to call you, but for now, let's give a one more round of applause to Dr. Kadam Pakeni and say thank you, and we'll see you all next week. Next week's seminar is live and in person in Phelps Lab. We have Dr. Yongying Liu from University of South Florida, who will be coming up and giving us a talk about large-scale estuarine and coastal hydrodynamic modeling. And so we'll be excited. And if, in fact, any students who might want to go to lunch with Dr. Liu, let me know, and we have an opportunity to do that. Cheers, everyone. Have a great day. It's beautiful out. Enjoy it, and see you all later.
Thank you.
Thanks.